There's my bio. I am on the principal code making panel 7, which deals with the National Electric Code. And we're going to be talking this first part about the National Electric Code for the U.S. For the 2026 upcoming code cycle. We just finished the second revision, so the things we're talking about today are going to be set in stone for the 2026 NEC. I know that the Canadian code does have some of these things in it, but not everything. The NEC, based on my study and over the years of the Canadian code, it's not as strict as the NEC, especially on some of the safety aspects, except for groundwater protection, and we'll talk about that a little bit because they're a little bit more strict on GFPE. Just to give you an idea about the U.S., there's 13 states right now that's adopted the 2023, and there's 10 more states in progress that's adopted. So by the first of the year or so, about half the U.S. states will have the 2023. In about mid of next year, we'll be printing the 2026 is what we'll be talking about. Just for kids and giggles here, I have projects, or my firm has projects in all those states. So we work across the nation from coast to coast. So we're diverse, and I'm traveling constantly for all those projects. But we do about 50% of our projects are saltwater type environments, and then we do land-based projects. We just completed this project. It's an engineering building, so we don't just specialize in marinas, but we do also do land-based traditional D&D. The 2026, which is this applies to both. Let me get out that speaker a little bit. Of course, we don't have a 2026 code book yet, but marinas deal in the NEC under Article 555, which is only about 2 pages of that book. It's not a very thick book. And if you think about how much electrical systems, which is one of the most expensive pieces of the marina, at least of the utilities it is, and it only covers 2 pages, but it's not. Because if you have, for example, a fuel dock, we go to another article, 514, to do with that. If you go to, then chapters 1 through 4 also apply. If you have electrical connections, it's 110.14. If you have electrical closures, it's .31. Branch surface feeders, 210. All marinas have a service, it's under 230. So all these codes of chapters 1 through 4, wiring methods, any listed wiring method that has an insulated grounding conductor is approved for marinas. But you look at chapter 300 for that. 400 is portable power cable, which is type G, type W, type GGC cable. So it's under 400. So all chapters 1 through 4 apply to marinas, but chapter or Article 555 can modify those chapters 1 through 4 for specific installations of marinas. And the scope, just real quick, and then we'll get into 2026. It deals with floating, also just not marinas, but floating buildings, 1 and 2 family dwellings. Just for example, do a lot of inspections on these for whatever reason. This is actually down in Alabama on Lewis Smith Lake, where there's this 15-year-old girl who was electrocuted, and I've done a lot of inspections down there. This is on Lake Erie Marina that I've done. It's about 1,200 slip marina in Buffalo. Also in outside the U.S. we work. This is British Virgin Islands. We got a project there. Got a project in Zuma, Bahamas. Got a project overseas as well. So we do work quite a bit outside the U.S. as well. Okay. As far as the definition, it also includes not only marinas, but also dry stack storages. So that's under Article 555. We designed dry stack storages as well, both just a 3-wall type open construction as well as enclosed. And this is actually me flying my drone up there on top, taking that picture. This is in Fort Lauderdale. This is another new facility just opened in Fort Lauderdale as well. It's the F3. I don't know if you're familiar with that project or not. It's a fabulous building. It's all automated facility. This is what the back side of it. This is what it looks like inside with overhead bridge crane. You top in an 840, and it's like a vending machine. It'll pick up your boat, put it in the water, and put your boat back in the slot. So it's a really cool thing to be able to pick up a 52-foot long, 30,000-pound boat, put it up in a slot somewhere on the top shelf. Okay, now into Article, the upcoming 2026. And this is right off the press. I mean, this is just got finalized last week. I was in LA all week last week finalizing some of these codes and some other articles as well. But the listing requirement, which is a third-party laboratory, but basically all electrical equipment shall be listed. And I'm not going to read the code. You can read it for you if you want to. I'm just going to highlight some items in it. But every piece, even ground fault protection equipment, everything has to be listed from a third-party laboratory. And there's many approved laboratories out there, so it's just doesn't have to be UL or one of the ones that we know about. But all equipment has to be UL listed. And then load calculations, and we have the small print is not changed, but we got C and D, which is talking about non-coincidental loads. And a non-coincidental load, if you have a boat with shore power, and for example, that slip has a boat lift, well, that's a non-coincidental load that it's either going to be powering the boat or you're going to be powering the lift. So whichever is the greater kilowatt hour is what we have to load. And this is actually down in Tampa, and you can see every single boat slip has a boat lift and it has a shore power. Well, these were real small shore power, so the boat lift wound up being the higher kilowatt hour, so that's what I had to load it by, not really leaving the shore power. So you ignore the shore power on that. So you don't have to build your huge service to be able to power the marina. You just power it for exactly what you need. So now in the code, 2026, it gives the HJ permission to say, okay, I can ignore that, or the engineer to ignore those smaller loads and only just do it for the big load. Helps out on the load service and the service sizes, so that will help the marine industry. And then also the next one is this power control systems, and you may not be very familiar with that because that's some new technologies that's coming around for power control. And within the electric vessel realm, which I've designed quite a few systems for electric vessels, those shall be permitted. And here under electric boat charging, which I do a lot of which that'd be level 2, level 3 if you want to look at that way. But there's smart load controllers and solid state breakers that are available now. And so here's a picture of one that I've designed this several times, where you can have each one of these breakers. You can see that's a 100 amp breaker, and you fit 12 of them in here and have a connected load of 1200 amps, but only have 400 amps on the input. So your infrastructure can only be there for 400 amps, but you can control 1200 amps on the output. So you could have 12 boats. Actually, you can even do that, but you can have these dual units. That could be 100 amps. So you could actually have 24 boats connected to this and charge 24 boats at one time, but the 400 amps would get distributed over the 24 boats. But then when several boats get charged and they go offline, then that extra capacity goes to the boats that are online. All the way down to the last 4 boats, and if you got the last 4 boats, you could literally put 100 amps into each boat. Because these are solid state breakers, and they do the load control, power control through those breakers, and they're smart. And also it could be a revenue. Just if you're thinking about doing something like this, you can put priorities on these smart breakers so that you have somebody that wants to have priority 1 boat. Say you got 4 priority 1s, and a priority 1 boat comes in. Well, it shifts power from the priority 2 boat to priority 1 and charges that boat first. And you can charge more money for a priority 1 boat versus a priority 2 or 3. So but if you just have all priority 2s and 3s and a priority 1 boat comes in, then he gets 100 amps and everybody else suffers until his boat's charged. But he's the one that's paying the money to have that. So it could be a revenue income as well. But that is a power control, and the NEC is going to allow those. They're allowed now, but just by the HJ saying that you can do it, it's not really written in code. But that's a smart breaker. You also can have 60 amp breakers as well. But that's one example of a power control system. Now, 555.9 is going to require, or has the opportunity of requiring engineering for marinas. And this is not mandatory unless the AHJ, the electrical inspector, says, I want to see electrical plans. And Up to this point, this has not been in the code, but engineering design is required basically upon request of the HJ, which is authority having jurisdiction. So if the electrical inspector sees that, well, this is a very complicated marina, or I've had trouble with the electrician that's here, he can say, I want engineered plans. And then the electrician, maybe through a design build, or the marina operator would have to get engineered plans. And the code making panel decided that it's not really fair for smaller systems like on the Lewis Smith Lake, where there's 15,000 plus, and it's growing every day, private residential docking facilities with only one or maybe two boats, very small systems that shall not be required for dwelling units if the voltage is 250 volts or less to ground, which that means that facilities like this was just right at the harbor here, where you just have one boat or another boat over there that would have to have engineering plans. And I'm going to go through this because I got lots of material to cover, so I'm going to just go through some of this pretty quickly. But bonding of non-current carrying parts, I'm going to go back to 2023 because, like I said, 13 states are adopting 2023 or have adopted 2023, and there's 10 more adopting. Electrical inspectors have misinterpreted what the intent of the code making panel does. If you look at this code, basically it says all metal parts, and there's a list of 3 items that have to be bonded, which is basically bonding is just connecting it to a wire so they're all at the equal potential, so all the same voltage. But there's a list of all metal parts in contact with the water, all metal piping, and non-current current carrying metal parts. And the trick is that what's likely to be energized shall be connected to the grounding bus of the panel with a wire not smaller than number 8. Okay, so the issue is the intent was this, and it's some grammar, I think, through the code making panel, and didn't do wordsmithing as well. But this likely to be energized has been interpreted only applying to this last item. So what inspectors were doing, especially some in Florida, was saying that all metal parts in contact with the water shall be connected to the grounding bus using number 8 wire. Okay? And the issue is that if you had a timber dock and the cross bracing down at the bottom, it had through bolts at the bottom, they were metal, they were in contact with the water, then every single through bolt was going to have to be bonded with number 8. Or if you have a concrete dock and you have some metal inserts or a metal plate somewhere that's nowhere even close to a piece of wire, it's going to make you bonded. And that's actually happening right now in Florida. And I've written articles about it and written city governments down there trying to help some of my clients and said, no, that's not the intent of the code. I'm on the code making panel. That was not the intent of the code. The intent is that if parts were in contact with water that were likely to be energized, then they would need to be bonded. And rightly so, because if they could be likely energized, then you'd want them bonded so that if they did become energized, it would create a fault current and trip over current protection. And if this even includes aluminum ladders. If you had a timber frame dock and an aluminum ladder on the end of a finger, and all the wiring methods were at the main walkway, there's no way that ladder was going to be likely to be energized by the electrical system. But the electrical inspectors were requiring that ladder to be bonded, which to me makes it more likely to be energized. So I disagree with that interpretation because that was not the intent of the code. So I submitted a public input, and this is what the 2026 says. Basically, it says all metal parts that are likely to be energized, period. If they're likely to be energized, then they'd be bonded. And we're going to say to the grounding conductor, but doesn't have to be greater than number 8. So that makes a lot more sense to me, and it has the intent of what the code making panel wanted to do in 2023. So we're trying to clear up and clarify some code issues there. Dot 14 has this equal potential plane, and what an equal potential plane is that one piece of metal is the same voltage as another piece of metal. So if you touched it at the same time, if there's the same voltage, then current won't flow through your body. That's what that's talking about. And here, this is around outdoor service equipment, and it basically in the following conditions, which basically is an equal potential plane that's outdoor service equipment, And both these conditions have to be true for this equal potential bond to be installed. And it's basically, if it exceeds 250 volts, which means it's a 277 volt 480 system, and it's within 10 feet of the water. I'm probably in some people's way, but I'm trying not to be able to have this thing squeal on me. So both of these conditions have to be true to be able to do this equal potential plane. And if these are not true, then you don't have to do it. That's what I suggest to do. Is many of my systems I design is a 480 system, and there's many 480 systems out there. Just don't install it 10 feet from the body of water, and you don't have to do this. And I'm going to go through this pretty quickly because it involves quite a bit of stuff to do it, but just don't install it within feet. But this is some of the stuff that you have to do. It encompasses the area around the outdoor equipment within 36 inches all the way around the equipment in all directions. And for example, here's a project down in St. Pete, and it's about 9 feet from the water edge. So in this case, that piece of service equipment right there is the utility transformer, and that is the service equipment. There's the meter. It's within 10 feet of the water, so we'd have to create an equal potential plane around there. And what that means is that the metal structure here and even the ground that you stand on has to have within 3 feet all the way around this equipment be equal potential. And you got several different types of material. You got concrete here and you got gravel there. Well, then this here would be the equal potential plane that you'd have to create. So any plane that you can stand around this, it has to be have that zero voltage around it. And there's different ways of doing that. You can have structural steel reinforced in the concrete for rebar, basically, embedded in the slab. But also in the gravel, you can do a copper grid with number 8 solid copper on a 12-inch center, 12 by 12 center, and that would be out in this space here. So you have to bond that 12-inch copper number 8 in 12-inch grid with the embedded concrete, and then bond it back up to the rounding bus, so that you're standing on stuff that is bonded. My suggestion is just move it back to the foot and you're done. You don't have to do that. Okay? So you have an engineer that wants to move this out here closer than 10 feet, slap his hand and say, no, move it back to 10.5 feet. You don't have to do any of this. Okay? And the reason, one reason is, and I want to talk about ground fault and understanding it. This right here is measuring leakage current up to 7,000 milliamps on this one surface. Okay, 7,000 milliamps, because every electron will make its way back to the surface, the point of return. So this is making its way back into, and actually I clamped the ground rod, and that ground rod had right at 7,000 milliamps of return leakage current on the grounded system. So it's really incredible. And that's one reason why we want to have surfaces that's close to the body of water have this equal potential plane, so it's safer. Yes.
This 7,000, is it the residual current collected from the entire dock coming back to that?
This had about, I think it had about 60, maybe 62 boats that served this was serving, and there was leakage current from those boats. Okay, and then areas not requiring this equal potential plane is basically anything on the docking facility. We're talking about on land, this is what we're talking about. This right here is the same article of just B. Okay, and then 555 by 35 for AC receptacles only, other than shore power. But if shore power is installed for a boat, it's required to have a GFCI maintenance receptacle of 15 to 20 amps. And Boat Safe, I really appreciated them having that maintenance receptacle. I told them about that. So they have a pedestal back there that has shore power. They have a 15 to 20 amp. And this right here is to alleviate extension cords and adapters and things that were just like I have right there. And this right here actually is a code violation. If you use something like this, or an adapter from 30 amp down to a 20 amp, it's a code violation. And actually this right here is not even listed for Marina use. Even though Marine Code makes it, it's a 30 amp twist lock, it's not made for Marina use. If you read the warning label on there, it's for RVs. And you have to have a 20 amp overcurrent protection, and it's always a 30 amp overcurrent protection. So that's a code violation to use those. And here, the pedestal does not have any 20 amp on it, so that pedestal manufacturer would have to now, because of this code, put a 20 amp, 15 to 20 amp maintenance GFCI receptacle on it. Force them to do that. Okay, this is, nothing changed in this, but I'm displaying this for a reason. This is Article 525.35, and it's where GFPE is required for feeders and branch circuits at not more than 100 milliamps. And the reason I'm doing this is because there's an exception that says that conductors of a separator drive system does not require to have GFPE. And that separator drive system can be the secondary side of a transformer. It can be a battery inverter. I'm having actually several projects having to put emergency lighting on docks that are covered to be able for egress. So if the power goes off, battery operated lights will come on for 90 minutes to help people egress off the dock safely. And there's state jurisdictions that's requiring that throughout some of the states that I'm doing projects in. So, but it's very difficult to put GFPE on an inverter. So as long as it's so that conductor is no more than 10 feet and installed in a raceway, we don't have to put GFPE on it. So it helps me as an engineer to have to be able to install these systems and do it very safely still. But that can be installed without GFPE. And then fire pumps. Does anybody have a fire pump on their Marina? Okay. Are they diesel or electric?
It's gasoline.
Gasoline, so okay, so it's what about yours? Is it electric or fuel?
Gas.
Gas, okay. Well, if it's gas, you don't have to worry about this. But I've had several, even in the past year, have to install electric fire pumps. Well, if you go down to the fire pump code 675, it says you cannot put GFPE in a fire pump because we don't want the fire pump to trip. But then we got electrical lines actually they're unfused conductors going from the surface to the marina up to the fire pump by code. So I got one code telling me I got to do unfused conductors to a marina and put ground fault protection under Article 555, but another code says you can't put ground fault protection. So what we're saying here is that under Article 555, the fire pumps we want them to be ground fault monitored, but not ground fault protected. And there's a difference. Ground fault monitoring is that we're monitoring for leakage currents. We're going to monitor for leakage currents, but we're not going to trip the power. Okay? But the ground fault monitor shall notify and have an audible and visible alarm that's located where it can be monitored by qualified personnel. That can be in a ship store, it can be on the dock with an audible and visible horn that just sounds that, hey, this fire pump circuit's leaking 100 milliamps. They go repair it. But we're not going to shut it down. So that's another piece that got put in there. And then under same 555.35E, this is a big one here, that coordination and performance testing is going to be required. For GFPE systems shall be coordinated, and what that means is that the upstream GFPE won't trip when a downstream sees a leakage current event. This is a big deal because I'm going in and repairing a lot of marinas that the main trips, when you got the main 100 milliamp will trip, but the 30 milliamp won't. And I'm going to show you this just real quickly. So you got the shore service. This right here is the disconnect on the shore. Then you got on the docking facility, you got a main distribution, say dock A with multiple shore power on it, and then dock B with multiple pedestals with shore power. Under the 555.35, it requires 30 milliamps on the shore power and 100 milliamps to protect all the feeders and branch circuits. Well, what's more strict about the Canadian code is that it requires 30 milliamps up there, and if you have 30 milliamps there, you don't have to have anything else downstream. Right? That's under rule number 78 of the CEC. So this is a little bit more lenient compared to the Canadian code, but it's still an issue because you don't want the main to trip, right? But what if you have a boat that comes in and you plug into that shore power, and that boat, I've seen water heaters, for example, pull 7,000 milliamps of leakage current because it had a crack in the element and it was leaking into the water system. So say that the thermostat in the water heater kicks in and it leaks, just say, 400 milliamps. Okay, what will trip? with the 30 amp trip or the 100 milliamp trip? If that boat instantaneously starts leaking 400 milliamps, okay, is that 400 milliamps greater than that? Absolutely. Is it greater than that? Absolutely. So what's going to trip?
I mean, ideally, point of use.
Ideally, it'd be local, right? Because then it would only affect that one boat, and that's what the idea is. If it trips up here, what is it going to affect?
The whole brand.
All of them. Now, how many calls are you going to get if it trips all of them? You're going to get a lot of mad people calling you because I got the power tripped out. Not only that, you won't know what boat it is. Because it could be any boat in the entire harbor and trip the GFPD. You don't know which boat it is. So you always want it to trip locally. So this coordination is extremely important. And what I mean by that is this. There's two ways to coordinate. You can coordinate with the sensitivity trip level, right? Which is that 30 amp or 100 amp. Go back here. What if this boat right here, say that boat instead of 400 milliamps, it pulls 40 milliamps of leakage current. What would trip? It would trip right there, correct?
Yeah.
Because that 40 milliamps is greater than the 30, but a lot less than here, so it would trip locally. That's what you want. But if it's greater than the 100, then you're in trouble. So here is a means of coordination because you got the different trip levels. So that is one means of tripping and making coordination. The other is through timing. Okay? How fast are those going to trip? Okay? Let me give you an example. Say that we put GFPE throughout the entire marina. Because you got plenty of money, you need to spend it somewhere, so we're going to put GFPE throughout the entire marina. Okay? Just go with me on that one. So you got 30 milliamps here, 50 there, 75 here, and 100 amp there. So a boat that comes in that pulls 40 milliamps, it's only going to trip there. But if a boat comes in and it's going to pull 60 milliamps of leakage current, it could trip there or here. Okay? If it pulls 80 milliamps, it could trip there, or here. Or if it about the 400 amp, it could trip up here and trip out the entire marina. We don't want that. Okay? What if we do this? Say that we can set the timings of when the GFPE systems trip. And so now, this is set at 75 milliseconds. That's at 100 milliseconds, 150, and 200 milliseconds. Now, say a boat comes in, plugs into there, and pulls 400 milliamp leakage current. What's going to trip? It's the one with the lowest and the quickest. Right? Because this will clear the fault at 75 milliamps and stop the leakage current at 75 milliseconds, excuse me. And so this right here is set at 100, so this right here will never see that leakage current long enough to trip that upstream current, that upstream GFPE device. So now this is fully coordinated. Now this was permitted in the 2023 code, but it's going to be required in the 2026 code. That's going to be a requirement to have it fully coordinated. Now you could just do it here and up there, which is probably what we wind up doing. Because you really don't need this intermediate, but this just gives you a graphic of what's going on. Yes, sir.
Are those coordination trip settings, are those customizable from the marina's perspective, or is that something that the manufacturers take care of? You
Generally,
just make sure.
The manufacturer.
Okay.
Depends on who you use.
Right.
There's some devices out there that are factory burn in as far as the trip level and the trip times. There's some that can be field settable.
Right.
And for this one, I don't mind it being factory burn in because it's set at 30 milliamps. I want it to be as fast as it can be.
Yeah.
Okay. I want it to be relatively fast.
Yeah.
Then I really would like for that to be field settable so that I can come out and I will test how fast those are, then adjust this to make sure it's fully coordinated. And I'll talk about some of that in a little bit. Okay, and here are some devices. This is actually from Bender with a 480 system coming in. There's the relay that's an RC MS490, which is a field settable relay. Here's the CTs that's doing that. I'm going to talk about the CTs just in a moment. So the GFPD has to be coordinated, and not only coordinated, but performance tested. Okay, so this assures that it's going to be designed, tested, inspected, and going to work like it should work. Okay? And this is actually me doing that performance testing. I've got crews that do that as well. But I got specialized equipment that I've done, and I travel with this cart all over the country doing performance testing. And it's a pretty involved process, but it works out quite well. I got the system down doing it quite well. But I'm going to give you some examples of things that I've found when I'm doing performance testing. Okay, and if you look at this is the CT, and in a moment when I go through understanding NEC leakage current, you'll see, and I got one guy smiling because he probably understands what's happening. The ground wire does not go in there. And no matter how much leakage current I produce on the ground wire, it would not trip. And I go up 100 milliamps, 200, 300 milliamps, and it wouldn't trip because that CT was never seen it because that ground wire doesn't belong in that CT. Here was a project out in Texas, and they did not wire the system like I designed it. They used common neutrals through multi-branch circuits, and they could not get the GFPE breakers to work. So what they decided to do, instead of making their neutrals bonded to the bus, like they should, and like code, and like UL and the manufacturer requires, this is what they did. They cut the copper off and left the insulation on to make sure that the power would stay on. And the performance testing, and the inspector didn't see this because it wouldn't be something that you'd normally look at. And it made it look like those neutrals were actually bonded to the bus, but there wasn't. This is actually criminal because when I went to every single 30 milliamp GFPE breaker would never trip. Even though it kept power and it looked like it was good, polarity was good, the hot neutral grounds were wired correctly, but it would not trip the GFPE breakers, and that was test buttons for them. So the performance testing and that was absolutely necessary. And because they shared neutrals, they had to take out all the wire for 3 different dots and rewire 3 dots. They tried to cut their corners, what they tried to do, and they wound up paying for it. Here is another CT, and guess what's missing there? The neutral's not in it. And this was very interesting because the contractor filed for substantial completion. I went out and was doing the performance testing, and before I started, the contractor said, well, what's wrong with this one substation? Because every single GFPE breaker will trip at night. And I come back in, I have to reset them all, I start doing my work, then come back the next day, every breaker's tripped. I knew instantly what was going on. I told him, you don't have the neutral through the CT, do you? He says, I don't know, I thought I did. And what was happening, what comes on at night?
Lights.
Lights, 120 volt light, which puts neutral currents on the neutral wire, which created an imbalance, and this thing thought it was a leakage current. So every time the light would come on, it tripped the GFPE. And the contractor would reset them in the morning and try to finish his work, the next morning reset them. Didn't even dawn about it, didn't even think about the lights when it's actually tripping it. Well, this was very interesting. This is actually, the wiring job is not bad. You've got 2 bender units up here, there's 12 channels. And what this does is you got the breaker 1, you got the CT 1, and you got a channel 1 up here. And what happens is that CT looks for leakage current. It will tell this unit, hey, channel 1 has leakage up above the set point, which is generally 100 milliamps in this case, and it should trip the shunt trip mechanism on that breaker and de-energize that circuit. Okay? When I started inducing leakage current, I would increase at 80, 90, up to 100, 110, 120, and I heard something. I heard like it tripped, but the circuit was still energized. What happened was, instead of the wiring going to here, it actually went to breaker 2 and would trip breaker 2 instead of breaker 1 and leaving my circuit energized, but tripping power on the neighbor's circuit. Okay? So what happened, it tripped breaker 2. And actually there was an electrocution that occurred, not on this project, but another project, where this actually happened, and leakage current was coming from here, but it tripped the wrong breaker, and actually there's an individual that deceased now because of this. So these are not just randomly things, these are actually cases that are major issues. So that's a problem. And you can see I was leaking up to 272 milliamps of leakage current on that circuit and it wouldn't trip. And in this case, this was in actually North Dakota, And this was about a 6 or 7 year old Marina when I was doing some renovations to it, and the harbor master said, Gary, why don't you come over here and just test this one for me? I said, oh, sure, I'll just do that, no problem. Well, it wound up, channel 1 would trip channel 2 would trip channel 3, and channel 3 would trip channel 1. None of it was wired correctly. So if you have a leakage current anywhere in that marina, your breaker was not going to trip. So you'd go out there and get electrocuted just at that. Here's another one that 40% of the shunt trip mechanisms failed in that one. And then no matter how much leakage current I would pull, it wouldn't work. Here, 1,000 milliamps doesn't work very well. Code just says 100 milliamps. Here's another one that the CT circuit was defective and wouldn't trip the breaker. Here's another one that leakage current it wasn't coordinated, so I could put in about 120 milliamps on the 30 milliamp, and it always tripped the 100 milliamp upstream and knock out multiple bolts at one time. So we had to make adjustments to that. Here, the GFE systems it was tripping the main breaker. This actually is the service equipment here, and it was stripping the main breaker, so they actually just disabled the GFE systems because it's such a nuisance. Because it kept tripping the entire marina out every time it tripped something. So the coordination is a very important piece. I find wire nuts off of control wires. There's another one off. Here's a wire that's completely off. We found one circuit not even wired. They said it's all done. Try to power up something and just, this one's not powered, and start pulling that wire, and there it is. The grounding system, this is a storm damaged dock. I redesigned the dock, had it wired, and we used an existing transformer to power it because transformer was still good, but the grounding system wasn't attached to the neutral, so we didn't have any path to ground back. So that was a fairly major issue to find, and luckily we found it. Here's another out in California that had a substation that would trip the wrong breaker again. So it's systems everywhere. And of course, what's the maximum limit on feeders and brake circuits? Milliamp wise, what is it, class?
100.
100 milliamps, right? Okay. If you look at this, now this is a breaker, it's a 200 amp breaker. That's the ground fault monitor system right there. If you look at the settings on this, the lowest it will go is 200 amps. Okay? Or actually the lowest it'll go is 40 amps. They had it set on the maximum. That's 40 amps is the lowest. So that's not even the correct GFE. The electrical inspector passed this. I don't know how. He saw the GFE device and they're okay, that's good, and went on. Okay, the inspectors don't know everything either. Okay, they just don't. I train a lot of inspectors. Matter of fact, I'm going to Michigan. I got, I don't know, maybe 200 inspectors. I have a class for the Sour State of Michigan in December. I just got back from South Florida teaching South Florida inspectors. I teach Tennessee and Kentucky inspectors. I teach them all over the place. But they're very grateful because they don't deal with marina code very often. So it's a good thing that I can do that. Okay, that's all the 2026. So how much time do I have? I want to get into 20 minutes. 20 minutes? Oh, boy. Okay. Remember I said that there's ground fault protection is very important. Well, there's two types of GFE. And I'm not going to get into everything that I wanted to do, but I wanted to at least do this. There is the Class A device, GFE, which will not supposed to trip below 4 milliamps and will always trip above 6. So at 4 to 6 milliamps is a Class A device. It's the same device that you have in your bathrooms, a test reset button, in your kitchen countertops, outside, any location in your house is this GFCI. And do not get that confused with the GFPE, because contractors have installed, where I designed a GFPE, they installed a GFCI. It's two different entities. A GFPE is anything that really trips above 6, and in the marina world, we have two settings, which is the 30 and 100. So the 30 and 100 are GFPE, ground fault protection of equipment. The GFCI is ground fault circuit interrupter. So there's two different devices. And they both have locations and homes in the marina. The 15 to 20 amp GFCI receptacle, which you plug the extension cords into, that's a GFCI. The shore power is at this 30 milliamp, and the branch circuit feeder is at 100 milliamp GFE. But I want to go through this class, the last part of this, understanding NEC leakage currents, as I've talked about it a lot. And I serve on expert witness cases as well, and I got 3 fatality cases that I'm serving on right now. 2 in Arizona and 1 in Florida. And some of those in Florida, there's some other non-fatality cases that I'm on. 2 others that on Florida that's been electrocuted but not fatalities. Okay, so for the marina industry to understand AC leakage current is an important thing. And if you look at this, this is really type W cable, but imagine that's a shore power cord. And this will be a 30 amp, 120 volt cord, because it's only 3 conductors. You got the black, the white, and the green. What does the black wire do for you?
Hot.
It's the hot, it serves power to the boat, right? What does the white wire do for you? Neutral. It returns power from the boat back to the source. What does the green wire do? It's the ground, it's the safety ground. Remember that equal potential plane, that everything that you can touch, that's what's bonded to that green wire so that you don't get shocked. Okay? And it goes back to the service, drives into the ground rod, attaches to the neutral of the service, and creates that equal potential plane, the equal voltage everywhere. Very, very important. If there is leakage current, generally it'll go back on that ground wire, or if there's fault current, it will go back on the ground wire, tripped over current protection, killing the power and saving your life. So that's a very important piece of cable or wire, is that green wire. So graphically, I'm going to open this table up. You got the hot, the neutral, which is the return, and the green, which is the ground. Okay, everybody understand where we are. Okay, it can be very technical, but I'm going to try to make it very, very simple for everybody in this entire class to understand the AC leakage currents. If you look at this, you got 10 amps going to the boat, and where would the 10 amps come back? Down the neutral. And this is a balanced system, right? Okay, so that's very good. On a 30 amp, it's not overloaded, it's perfect. You got 10 amps going to the boat, 10 amps coming back. Well, let me talk about this. I got this meter right here. If I clamp around that black wire, what will this meter read?
10.
10 amps, right? If I clamp around the white wire, what will this meter read?
10.
10 amps, okay? What does this meter read? What does it measure?
The magnetic field.
No, the measure resistance. What does it measure? We just said it.
The magnetic field.
Okay, that's perfect. Because it does not measure amps. There's no amps, no electrons running through this meter at all. It does not measure ampacity. Okay? There's a phenomenon, and it's called the right-hand rule. If you have a conductor and you put your thumb in the direction of the current and your hands wrap around the conductor, there's a magnetic field that goes around that conductor. Okay? It's a physical phenomenon in physics. That's just what happens. So every electron that goes through a conductor, it produces electromagnetic fields. So this meter is not measuring current, it's actually measuring the intensity of that magnetic field. And it's directly proportional to the amount of electrons going through that wire. Okay? So this is what it's measuring, is magnetic fields. It does not measure electrons, only magnetic field. And that's what and then it's just smart enough to be able to calculate the amount of amps that's going through that wire. So go back here, and that magnetic field is going in this direction because you got the right-hand rule, right? And it can measure the intensity of that magnetic field and then display it in amps on the meter. That's the right-hand rule. Well, what if you turn that around and you put your thumb in the other direction? Which way is that magnetic field rotating? In the opposite direction. But it's still magnetic fields that you clamp around the white wire to be 10 amps. Okay? If I clamp around that black wire, I'll measure the intensity of the magnetic field, which is displayed in amps. And so it'll be 10 amps. Okay? So I clamp around the white wire, I'd also see 10 amps. What do I measure if I clamp around both wires?
0.
Huh?
0.
It's be 0. Because if you think about the magnetic field, I got current and magnetic fields running in that direction and in the opposite direction, they cancel one another. So I read 0 if I have 10 amps going and 10 amps coming. Okay? Very, very important to understand that, because this is the CT that I've been talking about. Remember all the CTs that we've been talking about? So that's how ground faults are measured, is in this fashion through the magnetic fields. Okay? So in this case, I got 10 amps going and say I got 9.9 amps coming back. If I clamp around the black wire, what would I measure?
Yeah.
Clamp around the white wire, what would I measure? 9.9 amps. Clamp around both of them,
100 milliamp.
and say, I gotta have a balanced system, okay? So I have 0.1 amps on the green wire, but if we were to clamp around both of those, what would I read? I read 0.1 amps, because it's the differential, because I got 10 amps worth of magnetic field here, but only 9.9 amps worth of magnetic field there, so I read 0.1 amps, which is actually the 100 milliamps. Okay? So that is the CT that's measuring the differentials of those magnetic fields, and that's how ground faults are measured through all equipment. I don't care if it's a GFCI, if it is a ground fault device from Bender or from MEE or single device, or if it's from
Voltage.
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 Yeah. Thank you. But that's how you measure the leakage currents, right?
Yes.
It's exactly the same way through the differential of those magnetic currents. So that is the key to understanding AC leakage currents. And I just showed you this Fluke, which is about a $700 meter, by the way. Okay, it's a very, very nice meter. But you can't use this in what I'm doing if you're going to physically measure it. And I physically measure things all the time. This is not sensitive enough. Okay, there's not enough stuff going on in here above the measure down, because you get down to about a quarter of an amp, 250 milliamps, and this will go to 0. So if you use a meter like this and you start measuring leakage currents everywhere, I just get zeros everywhere. Hey, I got a perfect Marina system. You may not, because you'll be just zero, because it just doesn't, I'm going to say, doesn't measure down in the mud. Okay, down, it's not sensitive enough. So my go-to meter is one like this, which actually reads on here AC leakage current clamp. Okay, and this is a more expensive meter, but I can physically get 4 50 amp cords through there and measure them all at the same time. It's a little bit of a struggle. 3 is easy. Okay? 2 is all day long, 250 amps. So that's my go-to meter, and it's actually calibrated, and it's a technical term, dead nuts accurate. Okay, and it's at 30 milliamps, it reads 30.000 milliamps. 100 milliamps, it's 100.000 milliamps. And I keep it calibrated because of my expert witness work as well as commissioning that I do. That's the same meter that I do when I do all of the commissioning for all the marinas that I do as well. But they're not all created equal, and I have that meter, that one, and this one. Those are all the meter numbers. If you want to have those, you take a picture of that. But that's my go-to meter. That's the biggest throat. This one is way too expensive and big. That's about a $3,000+ meter. This is, I don't even know if they're making that one anymore. They might. I'm not going to find one. But this is about $1,100, $1,200 meter, somewhere in there. Then if you want to calibrate, another $500, $600 to get it calibrated. Okay? So in this case, if I clamp around all 3, what would I measure? Nope, I read 0. Because if you think about it, I got 10 amps worth of magnetic field there, 9.9 going in that direction, and 0.1 to make up the total of 10 amps going and 10 amps coming.
That's that example you showed first with the 3 wires through the CT.
That's correct.
That's always 0.
Yep. His comment was that this out here would be if all 3 wires are going through that CT. You'd never see the leakage current on the ground wire, and in fact, I'd read 0 milliamps. No matter how much I inject to the ground wire, it'd read 0. Okay? Now, does that click in your head a little bit? Okay? So, understanding that right-hand rule in the magnetic field is the key to understanding AC leakage current. Now, look at this. This is not actually accurate, but I teach it this way, that there's 2 types of leakage currents. There's really, really bad leakage current. Then there's lethal leakage currents. Okay? If the current is contained on the cable, okay, that's the best of the 2 scenarios. Okay? It's bad because remember, everything that you touch is connected to that green wire. You don't want current going through the metal that you can touch. And that's really, really bad. But generally it's not lethal. Okay? Generally it's not. Okay? It can be, but in this case, that 100 milliamps going through that wire, it's going to go through the path of least resistance and probably not go through you and your shoes or in the water, because it's just not as good a conductor as the copper conductors are. But that's really, really bad. But in this case, let me go through this, where you clamp around the two black and white wire and read that 100 milliamps. But then you clamp around the entire cable, which I do a lot, thousands of times actually, over the last decade, and I read current. What's happening in this situation?
There's the external influence.
What's that?
There's an external source.
Okay, because you think about it, there's 10 amps going, here's 9.9 amps going back. Is there anything on that green wire? There's not. That green wire has 0 amps on it. Because I'm reading a differential of 0.1 amps, and I can clamp around that wire and see it, but there's nothing here. So where is that current? It's got to be in the environment somewhere, because it's not on the cables. So in a marina, what's the environment? Water. And there's a really good chance that 100 milliamps is not coming back on that shore power cord. It's coming through the water back to the source somewhere. And generally, what is the source? What is the source? No?
Your feeder.
Generally, it's the utility transformer. Okay? If it's a 240 volt system, it's the secondary side, it's the center tap of the transformer, which is back on where? Land.
Yeah.
So if you're having current that's not on the ground wire, it's going through the environment, it's going through the water back up to the source, and every single electron, and there's 2.62 quintillion electrons flowing in 1 amp every second. That's 262 with 18 zeros on it. And they're traveling at the speed of light, which is 186,317.2 miles per second. Okay? They're traveling fast. None of them get lost. They all go back to the source. So if they leave the transformer, they're going back to the transformer. No electron will ever get lost. Okay, so it's going through it could be going through the metal. I've seen it on coax cable for communications. Okay? But most of the time, it could be going through the water. Okay? That is the second type of leakage current, and it's lethal. Okay? The electrocution cases that I have right now, there's people not alive because of this very thing right now today. So it's important that we understand what we're dealing with, and every one of us in here are dealing with that. Me as an engineer, you as operators, it's prevalent. And you got to really understand what's going on. At least I want you to understand what's going on. Okay? But now, there's another I'm finding in marinas, and I've dealt with this on many marinas actually, where you measure here 0, you measure there, well, see, now I measure that, which is 10 amps, measure here, which should be 9.9 amps. How can I take that back? Say you got 10 amps there, 10 amps there, and I'd still clamp around this entire thing and I'd get 0.1 amps. Okay? Now, I should have set it up a little bit better. But say I got a balanced system. I clamp around here and I had 0 amps, but I clamp around the entire thing and I get 0.1 amps. Okay? What's happening is I have additional currents on the ground wire. So just clamping the shore power cord and you see current, it doesn't always tell you the whole story. And what's happening is, and I've seen this several times, where I got a boat. And that boat measures 10 amps, in this case, going and coming. But I measure the ground wire, and I measure current on the ground wire. Then I go to this neighbor's boat, and I measure leakage current of his boat. And these are metal hull boats. And it could be metal pontoons or metal hull boats, whatever it may be. He is leaking current, and his adjacent boat has a really good grounding system on the metal hull, so those leakage currents are going through the water, getting back to that mother metal boat, and going through the grounding system on his boat. So if I start measuring leakage currents just by clamping cords, and I measure 3 or 4 boats that's got leakage current on it, then you have to isolate which boat it really is. Because there is a bad boat there somewhere that's leaking current that's transmitting to other boats and getting on the grounding system. So that's a very important thing to understand. But there's also some situations where the source of currents could be from other boats, but also could be another AC source. I've seen where some solar panels were creating some leakage current. Also, the service, but also there could be natural man-made currents. I've had a marina that had 2,000 milliamps on the ground current, on the grounding wire. 2,000 milliamps. We shut the main breaker off. No power on. We unplugged every single boat. 2,000 milliamps of leakage current. Had the utility come out and take the primary off the transformer. 2,000 milliamps on the ground wire. He went back a mile down the road and pulled the jack out of the overhead service and killed the entire neighborhood a mile around us. Guess what I had on the ground wire? 2,000 milliamps of leakage current. We could not get rid of it, and wound up. It was actually in Tennessee. TVA had a generating dam, and it was coming through the utility, through the ground, back up. For the anchorage systems, had dead men with stainless steel anchorage cables going out. And I was measuring 200 to 300 milliamps on the ground, on the anchorage cables, coming from the bottom of the lake. And that is a man-made currents in the lake.
Is that something that they address, or they just have to deal with it?
They just deal with it. I could not find any voltage gradients. I even experimented with my own body. I took my shoes and socks off and stuck my leg down in the water just to see because it felt first. Yeah. There's no shock hazard because it's just so wide.
Right.
So anyway, but clamping shore power cables is a method. It tells you something. It doesn't tell you everything. But if you want to start doing that, I'll try to help you get going on clamping cables because it does tell you a lot. It tells you the health of the marina. Okay, do you understand? You see some of my meters. I spend way too much money on meters, but I had one boat, a very good client that was wanting some help on the boat, so I was down doing some measuring on that. Okay, just real quick, some effects of the human body and current. We're talking about 6 milliamps, 5 milliamps, 30 milliamps, 100 milliamps. What does this do to you? And through the history of serving as expert witness, I've generated this table, and I've experimented on myself some. I have to admit that. Only in some small levels. Like I trained about my forearm down to my hand. This less than a milliamp, and it's a tingle shock. It doesn't really hurt. And you remember those tinge units for your back muscles and stuff. But less than a milliamp doesn't hurt. Okay. Now the 4 to 6 milliamps, which is acceptable as harmless to the human body because you can still move and boy, that hurts. I had 6 milliamps running on my arm, and it's all I could do to stand it. But I could move my hand. Okay, it wouldn't lock me up, but I could still move. If you get up around about 15 to 20, you get severe muscle, and if especially up around 20 milliamps, you got lost all muscle control, and your muscles will freeze up. And if you're in water and you get that much current flowing through you, guess what happens? Your whole body just freezes up. Okay? Your diaphragm is still pumping air, your heart's still beating, your mind's still feeling everything. It hurts like crazy because I've had kids screaming in the water because of electric shock at this level. Okay? It's extremely painful, and if you're in the water environment without a life jacket on, you have 20 to 50 milliamps flowing through your body, and you stiff up, what do? You sink. Like I said, your diaphragm is still pumping. And that's the term electric shock drowning. That you actually sink, but eventually you're going to take a breath. Either you pass out and the involuntary muscle, diaphragm will take over, and you're going to try to take a breath, or you're doing it on your own, but you're going to wind up trying to take a breath somewhere and your lungs fill up with water and you drown. Okay? And that's what's called the not let go current. Have you ever heard that? You grab something and you can't let go because it's too much current. Your muscles freeze up. That's what that is. And that's what causes electric shock drownings. Up around 50, your diaphragm starts having issues, and especially up above that, to 100 milliamps, is total paralysis of your diaphragm. That's electrocution. That's where the electric currents flowing through, enough electrical currents flowing through your body that it's affecting your organs. It starts to and physically electrocuting you. Your heart starts having problems up around 200 and 300. Your heart will clamp, and it's full electrocution time. Not a good situation. and your tissue burn is around 1,000 milliamps. That's only 1 amp. We're talking about 200 milliamps, 100 milliamps down in this area. Yes, sir.
I heard a rumor that they were considering, even for GFCI in houses, that they're considering moving it from 5 to 3. Maybe you've heard that too.
Yep.
You would know more.
So far, that's not. I've heard some rumors about that, but it's not in the cards yet. Even through probably 2029, that's not going to happen. Yes, sir.
Hey, I've had electrical stimulation therapy for back spasms and that before. Maybe others have as well. What would the range of current be for that?
Less than a milliamp, gentlemen. Yeah. Maybe a little bit more than that, but it's definitely under the 3 milliamps. Okay. As I said before, that's how many electrons are flowing every second for 1 amp. A lot of them, and none of them get lost.
One part that has been a constant experience just in the past year is people using the silver chloride measurement plates on their traditional multimeters. I've also seen these leakage detection floaties.
Yep.
Is this legit?
They do work to some degree, and like the shock alert or shock alarm, there's things like that. They have their place, but I think it gives you a false sense of security. Okay? For example, if say it's on a private doctor facility, and I've dealt with this many times, that they throw this little floaty thing out there, and the mother sees it down there. Well, it's okay. Kids don't jump in. Well, this is not a good situation, because if they're instantly, there can always be a problem, and your kid's in the water, you don't have to worry about that shock alarm alarming, because your kid's going to be in the water screaming their lungs out. It's too late by that time. So it's a false sense of security. You need the GFPE that will sense the current and de-energize at the same time.
Yeah, I can attribute to this one.
Sure.
One of, doesn't matter which Marina it was, install that we did for the pilot. Our leakage was detecting that it was significant, over 230 milliamps. But the person said, "Oh, well, let's try that boat." Let's verify. They threw one of the things in the water, no beeping, but
Sure.
it could be grounding.
It was still a ground fault.
It's still false.
And if you get between that and where it's grounding out, you'd be potentially.
Some that I've tested, I had lookouts, and I actually energized the water at 120 volts, had 320 some odd milliamps flowing, and this one detector said it detected up to 60 feet. So I went out about 70 feet, didn't detect it, went into 50 feet, didn't detect it, 40 feet, 30 feet, 20 feet, 10 feet, would not detect it. It would not alarm. I moved in about 4 or 3 feet, then it started barely ticking up, and about 2 feet it fully alarmed, pulling 300 and some odd milliamps of leakage current. And you think about that, is that dangerous? Absolutely. And this would not detect it. I called the engineer while I was on the call, found his number, and he says, "No, you're testing it wrong." I said, "No, sir, I'm not." And they wound up, and they had about 80 of these units installed on this one lake, and they had to fix everything. I actually pull resistors and capacitors off their circuit boards and actually fix it. And I never did go back and retest it. But to me, I'd rather have the true GFPE per code.
Yeah, because that can't lie. It is what it is. Exactly.
I know I don't have much time, but clamping cords, this is not a good example because you got a 50 amp and 230s on it, but you clamp both cords, you're supposed to have current going in and out. So here I'm measuring 27 milliamps. Is that per code? Actually, you sure? Yeah, it is, because
It's under 30.
Article 535.35B says 30 milliamps. Okay, so this is actually, it's reaching up there, but it is per
Still
code.
under, yeah.
Now, would that trip the GFPE? Probably would, because most of the ones I test are between 25 and 30 milliamps. So it could trip the GFPE still. Okay. What about 100 milliamps? Yeah.
Oh, yeah.
That's bad, right? Based on that chart I just gave you. 180, 280, and these are all true leakage currents. These are not where I got false ground currents, because I've measured the boats. All of these are actually true leakage currents where the boat was actually leaking current into the environment, water. What about 400 milliamps? Is that lethal? Absolutely, that's terrible. What about that one? Okay, almost 1,200 milliamps of leakage current on that one boat. Here's that same one with 7,000. Again, that's about 7,000 on there. What about this one? One boat.
Oh,
Almost 11,000 milliamps of leakage current. I don't care if you start your big toe in the water, you're electrocuted around this boat. No kidding.
I mean, at that stage, is it completely miswired? Like they're using
Now, what
Earth
happened
as
here
a...
is this was a boat that was winterized. He didn't want to winterize his boat, so he took the dipstick out of his engine and put in a 120 volt heater down into his engine block. And sometime over the winter, that engine, all the movement, the 120 volt heater shorted out against the engine block, had a very poor grounding system. It actually arced and disconnected the grounding system when it had fault current, energizing every single piece of metal on his boat, including the aluminum hull. And it was leaking about 11,000 milliamps and he wasn't there. And the dock harbor would not unplug his boat. About a week later, he called me up and says, Gary, we found the problem. That's what it was. But it's very, very lethal. And we're very fortunate that some of these did not cause electrocutions. Okay.
You got 20 minutes.
I got 20 minutes left? Are you kidding? I thought I had 20 minutes ago.
Every time you ask, it's another 20 minutes.
Okay, great. All right. Well, is there any questions on ground fault protections? I'm going to get into a couple other things. Yes.
What's your view on pen faults? Is this something that they're considering? I know there's a lot of discussion happening in Europe around that.
About what? I didn't.
Pen faults. If Earth and neutral get severed,
Yep.
there's no connection between these two anymore, and essentially would require a switch or a relay on Earth. You would
Right.
actually have to open up the Earth line as
There's
well.
been talk about, and what you're really talking about is ground fault monitoring. Or not ground fault, ground monitoring.
Yeah.
Grounding conductor monitoring, to monitor the grounding conductor. I've designed and actually had systems installed for ground monitoring, but then there's a cable. Everybody understand what top G cable is? Okay, there's that cable. Actually, that's almost a top G cable there. It's that rubber coated cable. Then there's the top GGC, which is a ground check, has a yellow bar in it. And that's used in mines a lot for that same thing, to make sure that ground and neutral bonding at the surface is always maintained, so we keep that grounding wire. That's not in the works for the NEC anytime soon.
Okay.
I'll just say that.
How significant does the risk change when there's salt water environment?
Okay, the question is about salt water, which is very important to this group. I understand that. Now let me ask this. I'm glad you brought that up. I'll use 10 minutes talking about this, probably 5 minutes. Okay, what's more conductive, salt water or fresh water?
Salt water.
I heard fresh, but salt water is much more conductive. Okay, salt water is much, now, knowing that, which is more lethal for leakage currents, fresh water or salt water? Okay, do you know why?
We're salty.
You're a better ground than the water.
Okay, if you think about it, okay, you already understand this. I'm very glad. Because a lot don't. But you think about it, if you out sweating or you tear and you taste your sweat or tear, what do you taste? Salt. Okay? And the salinity of your body is real similar to the ocean salinity. Okay? But your body is a little bit better and is not as good a conductor as the environment around you if you're in salt water because you got skin resistance. Right? Okay? Now you think about electrons in salt water, and say you got 100 milliamps in salt water, like we've been talking about, and you jump in that environment. Where's the electrons going to flow? It's like water downhill. They're going to flow what? The path of least resistance. You might get a little bit of electrons on you, but generally those electrons are going to flow around you because the environment around you is more conductive because you got skin resistance, and the electrons are not attracted to you because of the way that your makeup of your body is and the environment around you. Now, go back to fresh water. Fresh water was a very poor conductor, correct? And you're made up of salt, which is a lot better conductor. And you're saying you got 100 milliamps of electrons running in fresh water, and somebody jumps in or falls in, and you got 100 milliamps. Those electrons are going to travel in the path of least resistance, which your body is seen as the path of least resistance. So if you're in that water and those electrons, even though they're scattered out everywhere, those electrons will literally attract to your body, and you can have literally 100 milliamps flowing through your body because you're the path of least resistance. And therefore, that's why fresh water is much more dangerous as far as electric shock drowning than salt water. Now, the next question I always get is, well, why do we have to do this in fresh water, or salt water? Well, the NEC will never make a distinction between a saltwater marina and a freshwater marina. Because you think about just go back up in the harbor here. That you get a really heavy rain. That what happens to that water? It becomes brackish water at most, and it could have a layer of fresh water on top. Correct? So you think you got a saltwater marina, but you don't always have a saltwater marina. That there's times that it can be freshwater or at least brackish water, and that conductivity of the water drops. And if it drops below the level of the body, it doesn't take much. Those electrons will travel through the path of least resistance and travel through your body. And it happens quite often. So we cannot make a distinction between a freshwater marina and a saltwater marina when it comes to codes. Even the Canadian code doesn't make a distinction between the two because they understand what happens in the marina environments. So therefore, we got to have the same standards throughout both types of marine environments. Okay, good questions though. Okay. Anything else on ground faults? Then I'm going to move on to the last few minutes. Hopefully this has kept you awake during after lunch. Yes, sir.
Yeah, well, I worked with an electrical engineer in Alaska years ago who swore by, rather than grounding back to some kind of bolt or something on the shoreline, he swore by putting individual grounding rods on each pedestal down into the water. Comment on that?
Yeah, I don't see that that's a problem because you're trying to just create an equipotential plane even more. And think about how many people have underwater racing. The slip, we've got several hands that went up. Well, what are those made out of? Metal. Okay. And if you have a metal dock frame, which think about aluminum docks, do you put underwater bracing on some of your fingers? You don't? You got enough bracing there? And also the long fingers, which I got fingers that are 80 feet long, we have to put actually some intermediate bracing on some of those. And on a galvanized truss frame, which you don't do in a saltwater environment, but an aluminum frame or some metal dock structure, all that metal is bonded anyway. You got great big underwater bracing in water anyway, and they're bonded to the ground to zero volts. So it's no different than what he's doing. I wouldn't do it purposely. I don't think it helps. I think it's expense that you don't need. But it's not going to hurt anything. Yes?
Just a quick question around for slightly larger boats that maybe are doing 50 service lift phase that have their own generation on board. Sometimes, or even just a DC battery and an inverter, being with the cord color for DC, hot versus hot on AC. What do you see in the industry for a lot of mistakes being made when they're connecting up, or even just backfeeding to the end of the cord where maybe that switch that's supposed to kind of isolate when you have your generator on ends up backfeeding into the cord where someone could just touch the end of the prongs and get electrocuted?
And if that happens, it's an error.
And
what he's talking about is an onboard backfeeding to the shore power cord and getting someone in trouble as well. If that happens, it is an error. There's a problem with the electronics and the switching, and that should not ever happen. Because you need to, it's like an automatic transfer switch or manual transfer switch that disconnects the source to go to the alternate source, which would be a battery or...
do you see that error happen much? I mean, it
I
happened to me
on a
when I
boat,
was
I have
installing a
not.
pilot, and the boat owner, I guess it wasn't isolated, and I ended up touching just the prongs, and I got lit up nicely.
Yeah, well, it can happen because anything mechanically can fail, those switches can fail. What I see most of the time is that when it transfers over to a generator or an inverter, it doesn't open up the neutral ground quick enough. And it converts over to the shore power, and it still has the neutral grounds bonded together in the boat long enough, and it trips the GFPE system because it puts neutral currents on the grounding line. And I see that more so than a hot ledge not opening up. Okay? But I'm going to expand on your question. Is it safe to swim around your boat if you leave the harbor and you turn your generator on and your anchor, can you swim around your boat with 120 volt or 240 volt running on your boat? Is it safe to swim in the water? People do it all the time. Okay? And remember, when an electron leaves the source, it wants to go back to the source. And if it's plugged into shore power, the source is generally on the land. Okay? But if the source is on the boat, and the electrons leave the source, they're going to go back to the source. Right? So do you think the electron would want to jump off, run around the water a ways, and jump back on the boat when it can run through the copper on the boat? Generally not.
Isn't it that DC, if it's DC?
I'm talking about AC. I'm talking about AC. Say it's an AC generator, yes.
DC likes to go back to the battery.
Yeah, which is the source. It's still the source. Okay? It's the negative pole and source. So if your boat is out floating in the water and your generator's running, it's like a bird on the wire. A bird can land on a 7,200 volt wire and never get shot because it doesn't have a return path. This boat's the same way. You can run your generator all day long, swim around the boat, and be safe. Okay? Now, if you're at a shore somewhere and you park your boat and you don't want to, say you got a portable generator, so you move your generator on the shore and run the line back, then that could be a problem. Because now the source is on the shore and the current comes off the boat. Say you got a grounded islet somewhere and it's goes up 110 volts, those electrons will go back, try to make its way back to the source somewhere, through the environment. Yes, sir?
Question, what if it's fresh water? You've already been saying that a human body is a less resistant conductor versus the water, so if we went climbing out of a boat, water charged, instead of the water.
Well, those, if you think about in fresh water, they're not going to run around in fresh water very much. If you're talking about in a harbor, plugged in shore power, or
You were bringing up a scenario, if you're out in the middle of a lake or whatever.
yeah.
In this case, if it's fresh water, are you still safe?
Well, what's energized? And how does the water get energized?
Well, it's leaking through the boat.
Well,
You're saying.
but generally there's be no electrons in the water to be able to energize the boat because they won't go out because the source is actually on the boat itself.
Oh, I see. Just never goes out.
So it never goes out there. So it's very, very difficult to get energized water if you're not plugged into shore power. Okay. All right. I don't want to go through this, but if you doing a dock walk, or in my case, I'm doing a performance testing, and I see a lot of things. But remember the current carry metal parts, everything's supposed to be bonded. This is on a gangway bridge where you got electrical cables coming down a bridge underneath on a gangway. That bridge is likely to be energized, so it's got to be bonded. But you got a hinge point, in this case was the fifth wheel, that moves all the time. You need to be looking at those bonding wires, because I, just on one dock, had about probably 6 gangways, and all of them, the wire was disconnected from the movement of the dock. So that's your safety wire. It should be green, but in this case, you can see the lug right there.
It was once.
It was at one time. So look, I mean, if you don't have those bonded now for metal gangways, they need to be bonded, especially if you have electrical cables running out. So see if they're bonded or not. If they are, make sure it's intact, make sure it's tight. And I don't like this type of a bonding lug, because if this is moving back and forth, that will tend to want to rotate. My plans always have two bolts in the lug, so it won't rotate and come loose. So I would highly recommend replacing that with a 2-lug, and then make sure that's bonded. Cables coming out, and you need to do some just general tender loving care on wiring methods. Make sure that you don't have anything coming out. Fortunately, this is not rubbing up against that metal, because if it was, it'd be shorted out pretty quick. Okay, so just look at what how your wiring methods are there. Adapters, is that legal? Okay. Is anybody willing to raise their hand? Do you have these at your marina? Okay. What's the problem with this? There's several problems actually. One is it's not listed for marina. So if you have a problem with this, you're using an unlisted product, and the lawyers are going to really come after you. Okay. Another thing is, this is below the electrical data plane, and all electrical connections supposed to be above the electrical data plane. For a floating dock, it's 12 inches off the deck and 30 inches off the water. This is obviously below that. The biggest problem is this. What is that cord right there? Where's that? What is that? You know what voltage it is? It's a 50 amp, 250, 240 volt, 240 volt, 50 amp. That's a number 6 wire. So what are these down here?
10 gauge.
Number 10, 30 amp wire. So you got 30 amp wire protected with a 50 amp breaker. Do you think that's a problem? Can it be a problem? Absolutely be a problem, because you could have an air conditioner and a water heater, and that could be pulling 48 amps on a number 10, 30 amp rated wire, overheat, belt insulation, cause a fire, cause shock, and it's happened before, many times. Okay? So that adapter is not valid.
I don't connect it the other way.
Yeah. And the problem with that with GFPE, what he's saying is that he does it the other way. You have 230s and connect to a 50. Well, if you have the GFPE systems, you can have leakage current, actually not even leakage current, you have the neutral currents come in, the neutrals are tied together, split up to 2, and you can have an imbalance. You have more neutral currents on one side and the other, and trip the GFPE systems all day long. So they don't work very well either on the GFPE system. Okay? Again, this is what I mentioned right there. Those are the same thing. Even though they're made by Ring Code, they look like Marina, but if you look at, do I have that in here? There's one that's plugged in. There's another one plugged in, another plugged in, but look at that warning. Can you read that?
RVs.
What does that say? What's this made for?
RVs.
If you ask me, I vote is it recreational type vehicle.
Not under the code. There's an RV section called 551 for RVs.
Probably
Okay?
how they get away with it.
Vehicle, but not a vessel.
Yeah, fair enough.
Okay? And not intended for use in any other adapter. Adapter must be used in conjunction with what?
15.
50 amp. What's this plugged into? What is that right there?
30.
30 amp. Okay? And that's that same warning label that you see right here. Then you think it can get overheated pretty
That's
quick.
why they put it really small in it.
Yeah. And they're not listed for marinas at all. Yes.
So for the Y, just as one step back, do the Y split of 230s. In any case, if you have one of those 230 amp for the Y splitter, say the Marine Code cord, the other end should never be energized, correct? Or is that, because there's a product out there that has the 2, and there's a common theme here.
If you just let it hang in there, it should not be energized. Absolutely.
Yeah, so another common theme of me getting electrocuted. I was doing another install, and the prongs on that one, that one plugged in, one's not, and I go to grab the other one that's out, and I get.
You got a habit of grabbing energized components.
I was like, why is this electrified? And the generator wasn't on,
Yeah.
so it was coming back feeding. from
Yep,
the other.
exactly. You can.
Have you
Absolutely.
seen that?
I've seen that. Yeah.
Okay.
That's why I don't like adapters. So if you're walking your dock and you see adapters, think about these things. I'm not telling you to rip them all out, because if you have a boat that needs 230s, only got a 50, you're having to rewire something on your marina. But just be aware of it, and over time, try to get rid of them. Yes, sir.
90% of these are not owned by the marina.
Absolutely. Yeah.
Do you have a means of controlling individual owners who refuse to follow marina directions?
Well, I understand the issue, but whose liability will it be if it actually causes a problem or a fire or electrocution? You'll get wrapped up in it. So to some degree, you got to have control of what your tenants are doing. Okay, you do. It's not an easy thing to do. I'm not saying it is, because I've been involved with quite a few of them. It's not an easy thing to manage that sometimes. But just be aware of what can and has happened. Yes, sir.
It's a tough issue, right? Because,
Yep.
I mean, anyone can go on Amazon and get something from 3 or whatever in 2 days.
Sure.
Is there, I'm just curious, any of the harbors here have anything in their lease agreements or tenant agreements that state, you can only use?
I got some head shaking, yes, they do. And again, it's a management issue, and it's not an easy thing to deal with. Now, as we go on, this right here is something that you should be managing. Think about your mooring cables. They cannot interfere. There's a code, 31, that says this mooring cables can't interfere with the electrical system. But if you look at this, they can't, and these are covered docks, boathouses, whatever it may be, and they wrap around their mooring cables with the electrical. And you see it's already broke the conduit down there. And I see this constantly, everywhere. Okay? And think about how tight that is. You think it's damaging the electrical conductors inside that? Absolutely it is. Okay? And so the Smurf tube is it's not code compliant, but people wired them back in the day in marinas, and they get damaged. But you can see where the worn cable was. Look, they smashed it like crazy. What about this one? Or that one?
Nice.
Okay? Or that one? And it's everywhere.
I saw one that had the electrical cord actually wrapped around that. Would that cause anything further than?
Generally not. No, generally not. Okay, look at the type of cables that people are, homemade cables. And I'm not saying homemade cables are going to just disappear, but they need to be safe, okay, as you're walking your dog. None of this is very good, but the cable's really bad off.
That's a nice fiber one.
Okay? Don't open up the lids of your shore power pedestals every now and then. Okay, because the marina owner did not even know for this that they had done this. And look, do you think that green wire back there just hanging out there is a good thing?
Well, it was causing an issue on his boat.
Yeah, it probably was. Or they just hardwired right into the breaker here, didn't have a disconnect. And they never raise up the lid to look.
2 minutes, Gary.
10 minutes, right? And this happens a lot more than you think. There's another one, both of them. Even the breaker is missing on this one, so they're wired right into the bus. Okay? They kept tripping, so they just took the breaker out and remounted it. Like you say, tenants, they do some weird things. They do. Yeah, and you can't let them do this. This is just absolutely a no. Okay? And it happens over and over. And down here, even though the lid shut, it looked like the plug caps were there.
Oh, yeah.
They were smart enough to at least try to fool the harbor master, right? And again, I see it quite often when I'm going out looking.
That looks like the same facility, like someone gave it.
Yeah. Okay, and strain relief. Look at look at this pedestal. It's at a cantilever angle, right? Okay, and having plugs straight in is a problem, especially the 50 amp cords, because they want to bend down, and you start seeing things like this to hold it on.
Yeah.
Okay, and like this to hold it on. And this is what happens. What happens to that electrical connection right up here or here when it starts trying to pull out?
It's gonna arc.
You get a high resistance connection. And high resistance means heat when current goes through it. And guess what heat does? It starts melting plastic down. Okay? You got a huge voltage drop, starts melting plastic down, and it causes heat, it causes a fire. At best, it could cause electric shock at worst. Having plugs, does that meet UL wet listed ratings or plug straight up? No. Straight into it, straight down. I don't know why that's happening. All kinds of issues going on. And that's what happens. Because that was the top pin right there, had a high resistance connection, heated up, and luckily we didn't have a fire.
That wasn't a fire.
Well, it melted anyway, yeah. Smoke was coming out, I'm sure.
Looking back at the genesis of the L530 and its construction and design, to differentiate it from the RV plug, when you open up the female side, what was confusing to us is that the female blades are flat, yet the prongs are arced.
Yep.
So you get a point contact. You don't even get a
flat, good
it's
contact.
Perhaps the worst idea in any.
Then you put that angle bend on it like this, and it makes it even worse. Yeah. Wrapping it up. Let's see. Oh, let me go through this one thing. Portable power cable. Make sure that if it's through a metal structure that we got proper. This is we did a new boathouse. You see the PVC protected against the galvanized. The contractor ran it over here. Okay. It would have been real easy just to lay it in here and not lay it on the metal.
It's close enough.
Okay. And this right here, what can happen? Actually, they tried to put PVC protectors in, but they didn't do it quite well enough.
I understand the point of
And then Kelms grips, always make sure your Kelm grips are straight down, right? Because that's how they're designed, so it grips the cable. Do not let it all be supported right there, because these out here cables are all supported with that one little 1/8" strand of metal. Don't let this happen because it'll damage your cables constantly. See how tight band that is right there? Make sure you're doing your dot walk is there. This is terrible. This is not good. That's not good. Okay, that's not the way you support your cables. And if you don't even have Kelm grips, is that here's aluminum dock with a corner eaten halfway into the portable power cable right there. Okay, look at your marinas and the wiring methods, especially look under the dock every now and then. See what's going on. And even in timber frame, you got metal bolts and stuff you got to really worry about. If that rubs, it's going to damage that tens of thousands of dollars worth of cable pretty quickly. Okay, that's all I got. Well, I got a bunch more. Extension cords, is extension cords ever a good thing? They have their purpose, but they're not for permanent power. And I see this a lot. Is that a good thing on a marina? I'm very temporary. No grounding wire, right? Don't let those on your marina. Don't let these are dry top only. Don't let them on your marina. They're not wet listed. Okay? Very dangerous. Yes?
Real quick, could you go back to the wire hanger that was properly installed?
Here. Yep.
Okay, that would be straight up.
Yep. We want it here with that whole grip straight down in parallel with the wire. Yes, that's exactly what you want. Okay. Thank you very much. Appreciate it.